So let me start. Today I will talk about one important thing of the prospect of field theory, so which is algebraic extension. Okay. So what is algebraic extension? So whenever you have a field extension, uh, for example f and k over f. So there are two types of extension. One is algebraic, one is called transcendental. So algebraic means every element of k satisfies some monic polynomial, some polynomial, non-zero polynomial, is root of some non-zero polynomial of f. And transcendental means an extension which is not algebraic. That means k has one element which is not algebraic over f. Now, for example, q pi over q, that is not algebraic because pi is not algebraic element. So that algebraic extension has a huge role in the subsequent things in field theory like Galois theory and normal extension, separable extension, etc. etc. And transcendental equation sometimes used in uh, algebraic geometry and commutative algebra type of stuff in like in dimension theory. But here we will not talk about the transcendental extension. We will confine ourselves in in algebraic extension only. Okay, so let me define it formally. So suppose, so what is the definition here? First define. First let me define it. Let k over f is a field extension. Sorry, field extension. So an element, suppose it is alpha of k, is said to be algebraic. Algebraic means it satisfies some non-zero polynomial, non-zero equation. Algebraic if there is a non-zero. So let me write in this font for definition. Algebraic if non-zero polynomial let but any polynomial, suppose it might be px belongs to fx such that p alpha is equal to 0. Okay, in other words, alpha satisfies, or alpha is a root alpha is a root of some non-zero polynomial in fx. Okay, so it is clear. Moreover, otherwise, what is alpha said? If it is not algebraic, it is said as transcendental. said to be said and transcendental element of K over F. Fine. Okay. So there is, sorry, hidden transcendental element over F. Okay. Now the what is an algebraic extension? If every element of K is algebraic over F, the extension K over F is said to be an algebraic extension if every K is algebraic over F. I think that much you already know. So remember that every element means if alpha is an element of K, then alpha satisfies Fx. Beta is another element of K. Beta satisfies suppose Gx. Then F or G might not be same. Okay, I mean algebraic means they need not satisfy the same equation, but some equation. There exists some non-zero polynomial. Okay, some non-zero polynomial whose their roots. Okay, so first I want to give some trivial example. I already told you. Example. First example. Uh, every field is an algebraic extension. Okay, of itself. Second, q over pi over q is not algebraic extension. The next couple of example, just I am telling u root 2 over q is algebraic. Algebraic extension. Why? Okay, let me verify first. So, why it is algebraic over itself? Take alpha belongs to F, then it satisfies x minus alpha equal to 0. Okay, now the coefficients are 1 and minus alpha. They are already from F because I took alpha from F. Next, why it is not? Because pi belongs to q pi, but pi is not algebraic. Okay, Because pi is transcendental number, that proof is very hard to prove. Okay, it is out of algebra. It is some analytical proof. It is some historical proof. Okay, so it is not content here. Pi and e, they are transcendental number. That is, so they are also irrational number. Okay, pi and e, for e is being irrational. That is done in you can see Rudin's analysis book. That is done in very much elegant and easy way. Okay, but it is transcendental. They are the transcendental number. That is something out of scope of our syllabus. Also out of scope of algebra, you can say. But it is a standard statement we already know from our mathematical childhood period. Okay. Now we need to show that is an algebraic extension. Why? Because so what will be the elements of that thing? Q root 2, q square root 2. That will be a plus b root 2. Let alpha equal to a plus b root 2. So let me write down. So let first alpha belongs to q root 2. Then what is alpha? Alpha will look like a plus b square root 2, where a and beta are from elements of q. Fine. So I have to construct an equation, construct a polynomial or a polynomial whose alpha is a root. So see, for this I will just play with a and b and I will rationalize the coefficients. Okay, like now alpha minus a equal to b root 2, which implies that whole square alpha minus a square equal to 2b square. So 2b square, yes, which implies alpha square minus 2 alpha a plus a square minus 2b square equal to 0. Okay, so alpha satisfies. Now see, okay, now the constant term is this. This is a and b are from sorry, it is a and b. So a and b are from q. So this term is constant is from q. The constant coefficient is from q. The coefficient of alpha is 2 alpha, which is also from q, and it is 1. So it is already coefficient is 1. It is q. So the equation, so alpha satisfies the equation. What is the equation? X square minus 2ax plus b square minus 2b square equal to 0. And the equation, so alpha is algebraic. So I took any element alpha and so this is algebraic. So it is an algebraic extension. So just one reminder, this calculation, if I make any mistake, just feel free to know, because there might be some mistake in the calculation which I might not notice. So if there is some mistake, please don't hesitate to inform us. Uh, okay, so mistake might happen obviously. So uh, I think you understand the concept, how to solve. Again, but whatever q root 2 comma root 3 over q. You can show in similar manner. Is also algebraic extension. So again, for as long as much as we have discussed here, so you need to choose an arbitrary element, okay, and you will need to find out an equation which the element would satisfy, okay. That is the proper by definition way to showing algebraic extension, but that formula that might be some that might be hefty for this. Suppose I tell you root 2, root 3, root 5, root 7, root 8 over q. So is this algebraic or not? So that will be you need to consider a general element from that field, the bigger field which I just wrote there, vanished and then vanished. So the element itself look like a very big element. Okay. So and to find an equation will take more and more time, and you will definitely end with a silly mistake, and the equation will be no wrong equation, which equation we might want. So this by definition doing this is by definition finding an equation will be something very loadful task. Okay. So there will be some characterization of the algebraic extension. We will do one by one, don't worry. First of all, do some theorem, then we will try. First proposition. What does it say? Just a minute. Suppose alpha is, so there is no scene of field extension right now in that statement. Alpha is algebraic, so it is an element. F is a field, okay. Then there exists a unique, irreducible polynomial which is denoted by, we will call it as minimal polynomial, okay. In f inside fx such that alpha is a root of this polynomial, okay. Also, if you give me any other polynomial other than this, then this polynomial will divide the other polynomial. In other words, this polynomial, in other words, if fx in other polynomial, which alpha is a root, suppose f alpha equal to 0, then then this polynomial will divide this. In other words, fx has a factor this. Also, if fx is any other polynomial in fx such that f of alpha is 0, then m alpha of x divides fx. So in So you know already what I am trying to say. For example, okay, I am trying to say that suppose consider I over R. I is algebraic R. Why? I satisfies, I means square root of minus 1. I satisfies x square plus 1 equal to 0. Fine. But I also satisfies the equation x square plus 1 into x cube minus 1. Because that part will kill other thing. That is 0, so 0 into anything is 0. I also satisfies this term. Many anything into x square plus 1 will be satisfied by I. Any polynomial. Suppose it is fx, then also I will satisfy this. If you substitute I in place of x, I will satisfy this. Okay, there will be infinitely many polynomial that an algebraic element would satisfy. Okay, once you get this thing, you will multiply anything that will be its satisfying equations. Those will be its satisfied equations. But that is not my question. Okay, for example, for more clarification, I am saying that I satisfies this, so I satisfies all types of equation of this. See, so there will be tons of equations. For example, I satisfies these, I will satisfy this equation square. I will satisfy these equations over R, these equations over R. Sorry, a minute. No, these for sorry, just a minute. Sorry, these coefficients will not from those things. Okay, so I will take it as x square minus 1 because the coefficient will be from I, but if I take x cube, then I cube means minus I will be there, so that doesn't mean any source anything. So okay, no problem. So I will satisfy this type of equations. There is a subclasses x to the power 6 plus 1. For example, x to the power x square plus 1 into x to the power 2n plus 1. This type of equations will they also satisfied by I into any fx. Not all fx will work, but some fx will also work. So there are what I want to say that there are tons of equations that I will satisfy. But what is the minimum? So you can increase the degree according to your will, right? Suppose this is the 2-degree equation. This is the 6-degree equation. Okay, this is the 8-degree equation. This is something you can get a 10-degree equation that I will satisfy. Okay, for example, x to the power 10 might equal to I. Sorry, it will not be I. So for example, x to the power 12 will be I because x to the power I to the power 4 is 1. Yes, x to the power 24 will be I. So you can increase the degree x to the power 100 will be also equal to I. But what is the minimum? What is the minimum degree that and I will satisfy? This is this, and this is unique. You cannot get any other. You cannot get any other polynomial which I will satisfy. I will satisfy the higher degree, but not any lower degree polynomial than this degree to this polynomial. This is called minimal polynomial. Minimal means minimum degree of minimal polynomial of I over R. For example, if you consider I over C, then the minimal polynomial is this because the polynomial, the coefficients are 1 and minus I. 1 and minus I already belongs to C. But here it will be not an equation in I because I will not in R. So you need to push it until or factorize it until the coefficients are all from I. So minimal means given any field extension, take alpha from here, then what is the minimal, what is the minimum degree of a minimum degree, and that polynomial that alpha would satisfy? Which coefficients, and that polynomial will be coefficients from f. That is known as the minimal polynomial. I think I tried to explain that concept. Now I will formally write. I think you understood. I mean, if you fortunately get an equation, if you get fortunately get an say let alpha, you get an equation fx such that f alpha equal to 0, then you can produce tons of equations. Suppose fx into something, fx into, okay, fx into that square. The equation, if you take this equation, for example, fx er cube, see, alpha will satisfy also this equation, fx to the power 4. Okay, for example, x square plus 1 is satisfied by I. Then see, x square plus 1 whole square equal to 0 is also satisfied by I. X square plus 1 whole to the power 100 will be also satisfied by I. You can increase the degree by multiplying suitable terms. Okay, but the minimum one is this concept of minimal polynomial. So let me explain. Let alpha is algebraic over f, then there exists a unique, the minimal polynomial will be unique and it is be irreducible. You cannot decompose x square plus 1 in R. You can decompose over C, but in C x square plus 1 is not a minimal polynomial of I. And it is denoted as this thing, m alpha over f, such that alpha is a root of m f x. Also, if fx is any other that divides alpha, that's sorry, that has a root alpha, then that polynomial which I denoted by mfx, which is the irreducible of smallest degree. Irreducible means obviously it will be the smallest degree, because if you get another small degree, then you are decomposing, then there is not no more than no more irreducible. Okay, so then that thing, that polynomial sits inside fx. Sits inside means that will be a factor of fx. In the other word, that will divide. So let me prove. So first we need to show that existence of a polynomial. Let gx belongs to fx. Yeah. Such that g of alpha is 0. So that polynomial is our answer. Minimal degree polynomial is the monic irreducible polynomial. Unique irreducible polynomial. So as you watched that, alpha satisfies tons of equations. So I will ask you to suppose you are there 100 student. So 100 student give me one equation. Okay. Then I will choose the minimum degree. Who give me the minimum degree polynomial? I will choose his answer. So obviously gx satisfies some polynomial. If there is no minimal degree polynomial, then g itself will be minimal. So one polynomial is guaranteed. Gx will be there because it is algebraic. Okay. Such that g alpha is 0. We can assume that gx is a monic polynomial. Monic means leading coefficient is 1. Why we can assume? Because we are working in a field. Field means, okay, let gx is ax plus b. Then why? Then we can multiply g by the coefficient a plus. So gx is a inverse a plus a inverse x plus a inverse what is this? Ax plus b. So okay. So gx, if I take common a, then a plus a inverse b. So then you can work on this because this polynomial, sorry, if gx is ax plus b, then take common x plus b a inverse. Then see that thing still have alpha as a root. If you put alpha plus b a inverse, but a is invertible here. If the leading coefficient is invertible, obviously non-zero. So some non-zero coefficient will be survived there. So take that up to that. So it is a. Again it is a alpha plus beta. So alpha plus beta is 0 because z alpha is 0, so it is 0. So that part, the monic part will also satisfy the thing, so we can assume that g is a monic polynomial here. What I need to show that it is irreducible. So minimal degree will be always irreducible. Suppose we will formally show now. So suppose it is reducible. Contradiction, and we will produce a contradiction. Again, we will use frequent use of division algorithm. Okay, there is nothing but division algorithm. Suppose gx is reducible in fx. Then what is the definition of reducible? Reducible means it can be written as to product of two non-zero and non-unit. Then we can write gx as g1x into g2x, where degree of g1x and degree of the polynomial g2x are strictly less than, sorry, degree of gx. There is the irreducibility, right? So now put alpha both side. Then g alpha equal to g1 alpha g2 alpha. Okay, and obviously I'm reducible in fx, so and for your reminder, g1x and g2x belongs to fx. Now, but g alpha, it is g1 alpha and g2 alpha. Now, g1 alpha and g2 alpha, if we put alpha, then the x in the place of x we are putting alpha. So by product and sum, power product and summing the polynomial at alpha, evaluation at alpha, we will get an element in belongs to f. That will be also an element belongs to f, and that is 0. So product of two element of f is 0, but the product of two element of f is a domain. So either this should be 0 or this should be 0. So this thing implies that either that is g1 alpha g2 alpha equal to 0, and if is a domain. Implies that either g1 alpha is 0 or g2 alpha is 0. So if g1 alpha is 0, sir, what is meaning by this? Meaning of this, that implies either g1 or g2 has a root alpha. Okay, but what is the problem then? I assume that g is the smallest degree polynomial. So if g1 or g2 has a root at alpha, then g1, the degree of g1 and g2 both are less than degree of this. So I can find a smaller degree polynomial than g which has a root at alpha. So this is a contradiction because I started with g to be a minimal polynomial, minimal degree polynomial. Thus gx is irreducible. So we get the irreducible polynomial here. Now what I need to show? So here him if ax is the minimal degree polynomial. So I need to prove if this is, I mean, any other polynomial would be, if any other polynomial, if suppose if x divides, if has a root at alpha, then then the minimal polynomial here, which is gx, the minimum degree polynomial gx would divide f. Okay. Then I will show why it is unique. So first we prove the existence part. This is existence. Okay, I will. Sorry. This is existence. Okay. There exists. So this part is existence. What is existence means? What is the choice? What is the choice or construction? This is called existence part. Now we will prove the uniqueness. Uniqueness has not been established and this part is not been established. So we first prove this part, then with the help of this we will prove this is unique. Let fx be any other polynomial in fx, okay, that has alpha as the root. Then obviously apply division algorithm. So then there exist ux and rx such that fx equal to gx qx plus rx, where rx is the remainder. So if rx equal to 0, I mean the remainder is 0, then fx equal to gx qx. It might be 0, if not might be 0. Okay. Then fx equal to gx qx that is gx divides x. That we need to show, na? Gx will divide f, and we are done. But if suppose Rx is non-zero, then if Rx is non-zero, then the division algorithm what says what? Degree of Rx is strictly less than degree of Gx. Now, if we put alpha both sides of this equation, now f alpha equal to g alpha u alpha plus r alpha implies, see, alpha is root of g because g is the minimum degree polynomial which satisfies alpha. G is the minimum degree polynomial which has a root alpha. I mean, it is satisfied by alpha, and f is any polynomial that has alpha as a root. So both equation, both polynomial is satisfied by alpha. So this is zero. This is zero. This is zero means the whole product is zero. So it is zero equal to r alpha. Imply that r alpha equal to zero. But we choose g to g is the minimum degree polynomial. Okay, I'm writing here. This contradicts our assumption that g means gx. Okay. So, and Rx in fx, okay? Because the division algorithm, g is minimal degree polynomial in fx. In fx. So, Rx equal to 0 always. That means we are done. This is impossible case. Next, we need to choose minimal polynomial is unique. So, suppose, so it is clear from this. Suppose there is another smallest degree in fx such that uh, name the polynomial hx. Polynomial hx belongs to fx such that h alpha equal to 0. But already g is the smallest degree, g is one of the smallest degree polynomial, and from this thing, we can see that if any polynomial has a root at alpha, then gx will divide this polynomial. So gx will divide hx. just put above gx divides hx. That means there is something, suppose gx equal to, sorry, hx equal to gx into some k1x, where k1x belongs to kx. Now, if we proceed the same thing, what I have done so far with hx, see, and start the proof with hx, then we can say that interchanging the role of h and g, also hx divides gx, because hx is a smallest degree polynomial, and here now gx satisfies alpha, so h is also divides gx. Interchanging their roles, we can say gx is also divisible by hx, hx into k2x, where k2x belongs to x. That means, what is that means? That means hx. Now put this value of gx here, equal to hx k1x k2x. If you crossed, fx is an integral domain, so you can cross. That means k1x k2x equal to 1. Okay. That means, what does that mean? They are individually equal to 1. Because, see, that is a polynomial and that is also a polynomial, and we are in a field. So what will that will, I mean, if you assume and expand these things, like k1x is equal to a polynomial and k2x is another polynomial, and both devise these things. So okay, first they are scalar. Okay, now observe that from this line, degree of h is greater or equal to degree of g, because if we multiply gx with some polynomial, then we are getting equal to getting h. So degree of g plus degree of this polynomial equal to degree of this. So degree of h is greater than equal to degree of this. Degree of gx. You can put a bracket or avoid also. Degree of gx, degree of hx. And also from this line, we are getting the reverse thing. Degree of hx is greater than degree of gx. Greater equal to, less equals to. That means they are actually equal, which will imply degree of gx equal to degree of hx. But then, if degree of this is degree of this, then k1 is a scalar. Also, if degree, also from there, degree of this is equal to degree of this, So K2 is a scalar because if it is not scalar, if it is some non-zero suppose x is there, so its degree is increased by 1, but its degree is exactly equal to this. So it is not, it is impossible unless it is a scalar. That means that is uh, k1x, k2x are both scalars. So assume k1x equal to c1, k2x equal to c2, where c1, c2 belongs to A. Observe that we started with without loss of generality whatever we have wrote. Now we will use that it is a monic polynomial. We started with the monic polynomial. Okay. So it's what is its hx? So its leading coefficient is 1. Its leading coefficient is 1. So what is the leading coefficient of hx? It is something like c1. And what is the leading coefficient of this thing? Hx. So okay. Also, you can assume that hx is a monic polynomial. No problem. There is no harm to assume that they are monic. There is no harm to assume they are monic because we can. I told you earlier that any field polynomial in fx can be converted into monic by multiply the inverse because in field every non-zero element has an inverse in f. So okay, it is not done yet. As gx and hx are monic polynomials, then it implies so its coefficient is 1 or leading I mean every that thing and its coefficient is 1 leading coefficient. So and this is a c, so if you compare c into something is 1, sorry, so it is c into this thing is 1, c into coefficient some 1 is 1. So what is c from the leading if you compare the leading coefficient? Okay, so the leading coefficient, I mean, they're same degree. It is x to the power n, there will be also x to the power n because I showed that their degree are same. So it is the leading coefficient is c here, the leading coefficient is 1 here. So c1 is 1, similar to c2, c2 is 1 because c1 into c2 is again 1. So c1 equal to 1, c2 equal to 1. I'm directly writing. So this is proved now. Now, as a corollary, we can write this. Now there is comes the scenario of field extension. If is an extension, a field extension is, is a field extension and alpha is algebraic over both of f and l. Both. Okay. Now read this much. So alpha is algebraic over L, uh, and alpha is also algebraic over L. So alpha will satisfy, according to the above theorem, a, a minimum degree polynomial over L. So alpha will also satisfy a minimal degree polynomial over L. Also alpha will satisfy a minimal degree polynomial over F. Okay. Now suppose this is the extension. F is the base field and L is the upper, the upper field. And so suppose alpha satisfies here fx, the minimal degree polynomial. Suppose alpha satisfies here gx. Now, is there any relation between fx and gx? Is there any relation between them? The answer is fx will divide gx. That means the minimal polynomial of alpha in the bigger field, the relation will be converse. That that should be according to the intuition. The minimal polynomial of the lower field that might divide the minimal polynomial of the upper field of alpha. But the theorem says that no, it is wrong. The minimal polynomial of alpha over the bigger field, the minimal polynomial of the alpha over the bigger field L, that will divide the minimal polynomial over the minimal polynomial of alpha over the smaller field F. So what is the intuition? I am giving you first the intuition. So L over F means, so there are some extra element you can say that, roughly assume, it is not correct always, but roughly assume that L is made of F adjoining some element. So you can assume that there is some roots of or conjugates of alpha, or in particular alpha is there. So more elements are available. So as more elements are available, so the degree of minimal polynomial will decrease. For example, what is the minimal polynomial over q root 2 over q? That is x square plus 2. Sorry, x square minus 2. But what is the minimal polynomial of q root 2 over q root 2? That is x minus root 2. So more elements are available. Root 2 is available there, but root 2 is not available there. So root 2 is available not there, so I need to increase the degree. So rationalize the coefficients. That is the intuition. So we are increasing the degree, but we don't need to increase the degree here. So in that case, that properly divides this. Okay, the intuition is clear by the example. So let me write it properly. Then you remember the notion m of alpha L x. That means the minimal polynomial of alpha over L divides minimal polynomial of alpha over fx. So minimal polynomial, sorry, I am again saying that minimal polynomial or minimum degree polynomial depends on the base field. On the base field. Yes, okay. The minimal polynomial over I over C is x minus I. Because we are taking over C, the coefficients would come from C. But it is over R is x square plus 1 equal to 0. So change, that change. See, that change. it will divide, but where the quotient will be there in Lx, in the bigger field, because after dividing what we are getting that might not be available in the lower field. For example, the example I stated few minutes ago, I in C, the minimal polynomial is x square x minus I over R or Q, it is x square plus I. Okay, see, that divides this thing, x minus I divides x square plus 1. And after dividing, you will get x plus I. But x plus I does not belongs to qx. But it is readily available there in cx. To cx. You understand why that happens? That is by an example, okay? But by an example, we cannot prove a theorem. So we need to proceed by logic. Okay. So proof is directly from here. How? Okay. See, m of alpha comma f x is a, this is, so in Lx, okay, I am writing as in Lx we are getting two polynomials having, one is obviously this polynomial, it is the minimal degree polynomial of alpha over L. Another is, why I am getting inside Lx, because this thing belongs to actually fx, right? The coefficient should come from f, but f is, L is an extension of f, so extension means first of all said theoretically it is a subset of L, so that belongs to Lx. So the coefficients come from f, but f is already contained in L, so the coefficient I can take coming from L. But this is the minimum degree polynomial of over L. I am considering over L. Over L, this is the minimum degree polynomial, that is any polynomial. I don't know whether it is minimal degree or not. In F, this is minimal, but in L, I don't have any idea. Okay, no problem. Don't have any idea. So minimal degree will divide this by above theorem, by this theorem. So this divides this. But m alpha L x is the minimum degree because it is unique. We have proved. Polynomial Lx that that root alpha. So I have a theorem. Yes, divides and it's proved. Okay, you understand, I think. So definition, I am formally now defining what is minimal polynomial. I have, by in the context I have told many times. The the polynomial, because it is unique, we have proved. The polynomial of, okay, let me formally define that alpha be uh, algebraic over f, then the smallest degree polynomial fx belongs to fx. Okay, polynomial which has alpha as a root is called the f, and is denoted by fx. Okay, so I am again saying, suppose in if one satisfies x minus 1 equal to 0, but it also satisfies x minus 1 to the power n is 0. So I can increase the degree. So how, but the how much I can decrease the degree of that polynomial, that is called the minimal polynomial. Up to how much, and what is the resulting polynomial here? Okay. Now it is a degree. That degree is sometimes called the degree of alpha. The degree of the minimal polynomial. Sometimes it's called, sometimes is called that the degree. I think over f. Over f, I mean, if there are one field, then you need to mention over f, and if there are two, there is no need to mention if one field. If there are two fields, then you need to mention over which field. Okay, because you already noticed that the over two field they might have two different minimal polynomials, so the two different degree will be there. Okay, just a minute. Next theorem, proposition 11, which is according to Damit, what I am just a minute. There is a proposition, which is the observation. Okay, that is not something like heavy. Just a minute. I am writing in shorts. You know all the notations now. If alpha is isomorphic to if x quotient y, okay, and if what is that? This is the vector space combinations. But the field F, this is actually we have the minimal polynomial, which is degree of alpha by our above things, by our definition, because we defined this thing as degree of alpha. This thing and this thing are same by this theorem. So we need to prove that. But there is nothing to prove because we already shown that in the previous lectures or previous classes. Yes, this thing. This is already shown. What was Px? What was Px? Px was, what was Px? Px was irreducible polynomial and alpha is a was a root of Px. But here same thing. Here Px equal to max. See, what was the choice of mfax? If you notice in the theorem, it is actually Px. That is the fun. Unique, monic, irreducible, that we need to show. So we choose that. That is, I mean, that is unique irreducible polynomial. But what is the irreducible polynomial? The minimal degree. So mafx, what we have choose, it is actually Px here. So we can substitute or we can treat this as this thing. But I am again saying in the previous what I have shown to you, what was there? That was, I think, the irreducible polynomial. Okay, but what is the choice of irreducible polynomial here? That is the minimal polynomial or minimal degree polynomial, which was mafx. So the choice of px was this thing. So I can substitute this in that previous theorem and I will get this thing. So that is clear from that is clear. I am not going into this. Huh. And why the degrees are equal? Same. Why the degrees are equal? That also follows from there. If the degree was if this was in degree, then that will go up to n minus 1. The degree will, I mean, same degree. The degree of px is there and px is there m a comma f of x. M a comma f x. So that will be same. So I'm not writing explicitly, I'm writing is that clear? So I think you understood this. Again, some example. Examples. I also already gave some example there, right? I gave some example of algebraic or non-algebraic. The minimal polynomial of root 2 over q. First, we need to notice whether it is algebraic or not. It is algebraic, so there exists some polynomial. If you are struggling to find any minimal polynomial, that polynomial which some that satisfies some non-zero polynomial that might also serve. Okay. So the minimal polynomial over q is x square minus 2. And what is the degree of extension? Okay, you can also by manually we can think 1 comma root 2 because a plus b root 2 is there. Any element will look as a plus b root 2. So which will give the basis 1 comma root 2. The degree of extension is the vector space dimension. There are two elements in the vector basis 1 and root 2. So from there we can say that it is 2. I mean u root 2 actually is u plus root 2 into q. So this is this is 1 comma root 2 implies dimension equal to 2. But from this thing, what we can show that what is the degree of minimal polynomial 2? From there you can also conclude the dimension in that thing is 2. But another way, it is one way, it is another way. It is degree of f is q, x is root 2, alpha is root 2. Sorry. Degree of m of alpha comma f. Alpha is root 2, f is q, it is x. But degree of what is this thing? This is x square minus 2. This is 2. So the two answers matches. This is 2 or this is 2. Equal. So you can solve anyway. Actually, this is irreducible. Why this is minimal polynomial? Why? Because irreducible. Also, or by zero test, because it is second degree polynomial. So we know that reducibility or reducibility over a q depends on whether for degree 2 and degree 3 only, depends on the polynomial has a 0 inside q or not. For degree 2 and degree 3 only, okay? for degree 4 and onwards, it will not be there because x square, x to the power 4, something, what is this? Some, there are counter example, right? That might not have any zero in Q. For example, x square plus 1 whole square. That has no zero in Q. Degree 4. It is reducible, but because it is x square plus 1 into x square plus 1, still has no zero. So degree 4, that will not work, but degree 2 and 3, that will work. So this is degree 2, we can use the zero test. Or Eisenstein. Eisenstein is very good. In general, what is this thing? Nth root of 2 over Q. See, nth root of 2 satisfies this equation in Q. Satisfies this. So it is irreducible by Eisenstein. So this is irreducible. I think 2 will work. P equal to 2 might work. So it is irreducible and and root 2 that satisfies that equation x to the power n minus 2 equal to 0. So this is the minimal polynomial. So what is the degree extension? This is degree of minimal polynomial of nth degree root 2 over q x, that is. But wait, it is the minimal polynomial, degree of minimal polynomial over the same field. There is one. Because the minimal polynomial is same. Because that is available here in the base field. So I can treat this is the minimal polynomial. And degree 1 polynomial. So I cannot further decrease the degree. Because this is non-zero element. So I need a non-zero polynomial. Okay? Sorry. Then I need another a couple of theorem to conclude the proposition to conclude this class. Proposition. So I have told that when there are some conditions to check whether an element is algebraic or not. Okay. So there are, suppose I gave you that element. Suppose I gave you that element. Root 2 plus root 3 plus root 5 plus root 7 plus root 11. Root 11. So I told you, see that elements in algebraic over Q or not. If it is algebraic over Q, why it is? So then you need to find out, you are worried and need to find out even that case. Suppose root 2 plus root 3 plus root 5, its minimal polynomial over Q is hard to determine because if you alpha equal to root 2 plus root 3 plus root 5, you can do this way, then alpha minus root 2 square equal to 3 plus 5 plus root 15. Then, I mean, how to determine, this is one way, 2 root 2 alpha plus 2 equal to 8 plus 2 root 15. Okay. So it is alpha square if you take 2 alpha plus constants are on the other side. So it is minus 6 equal to 2 root 15. Again, you are doing square here. If you are do square here, then there will be something. Then one third will be eliminated and something will be left. So suppose I give you I give you an extra element. Then there will be more hefty process. Then there will be more hefty process. So how do you know it is algebraic or not? There is an according to the relating to this the proposition is there, which I am going to write. The element alpha is right over it if and equivalent condition. So it is characterization. Sometimes if and only if is called as equivalent condition. Sometimes it is called as necessary and sufficient condition. Same name. If and only if the extension. So it is a field extension. I am attaching alpha and constructing the field on f and alpha. Simple extension. Why it is simple extension? Because this type of extension, which is attaching, I mean, it is not okay. It is generated by f and one element. There is a simple extension. It is called simple extension. I defined in previous classes. The simple extension is finite. So what is finite extension? Finite extension means if you consider f as a vector space over f, then the dimension of the basis, I mean, so the dimension is vector space dimension is finite, or the cardinality of the basis element is finite. Okay. Also, we can say whatever we can note say. Just a minute. So, if alpha is an element of extension of degree, that means vector space dimension is n. A polynomial degree at most n. It might satisfy equal. So if alpha is an element of an extension of degree n, no. Actually, just a minute. That is unrelated. Alpha is an element of extension of degree. It means there is a vector space extension of f k. I am taking any element from k, which is, I mean, belongs to that extension. Because if my first word was true, then at most will not come. Then exactly will come because extension degree means exactly equal to the minimal polynomial. Okay. And if alpha satisfied a polynomial in f, that I can say less than equal to 12. It is also very straightforward proof, nothing difficult. First, we need to show this part. Alpha algebraic, then that is finite extension. So first I assume that alpha is algebraic. Wait, alpha is algebraic over F. So it is algebraic over F. So it satisfies some non-zero, equation. Then what I need to show that the extension is finite. Then what they can. Then alpha satisfies that equation is there already. Satisfies m alpha comma if x equal to 0. That equation is there. But I need to show the this is finite extension. But what is this? This is degree of this. I have just told there by previous theorem. Already, I think. By previous theorem of already. Proposition. But this is equals to this by previous proposition. What is the degree? Degree is obviously finite. Polynomial never, never infinite degree polynomial. Polynomial obviously terminates after some degree. If it is infinite, then it is called power series, which is not a polynomial. Okay, finite. So the extension is finite. We need to show the converse thing. Firstly, if the extension same, it will come from this line only. This is the connecting line. If this is finite, if this happens, this is finite, then this is finite. And if this is finite, then as this is equal to this, then this will be finite. If the extension firstly, if the extension just a minute. finite mean I need to take an element alpha from that extension. What I have just what is that? Huh, that thing. I need to show this. That will give the only if part. So in general, I will take an element alpha from that from the extension. That is the more generalized version of the only if part. That is precisely. That is not different statement. That is precise statement. That is not different statement. Okay. Precisely means particular or generally. Conversely, suppose alpha is an element that is not, you cannot take, I mean, that alpha. That might be some different alpha, but element of an extension. That means there is some alpha where alpha belongs to K and the vector space dimension of K colon F is N, right? So degree extension N, so any N plus 1 element will be linearly dependent. Vector space dimension is N, then uh, I can take upon this thing. I mean, you might wonder why I took if part and that then precise part. The only part is the precise that part. So it will satisfy some equation. So there exists coefficients or linearly dependent on which field that I need to mention. Right? F, because degree over F I am doing the algebra. So there is coefficients D0, D1, Dn, not all zero, not all zero. That is an equation of linearly independency. But that in turn says that alpha satisfies the equation. So you can also, I mean, elaborately there is B0 plus B1 alpha power or Bn alpha power n plus Bn minus 1. That means that belongs to F. Okay. That means alpha satisfies z terms with square alpha satisfies addition bnx to the power n the polynomial, sorry. And we are done. Okay. Now alpha satisfies this, which is n degree polynomial. Okay, no problem. But alpha might satisfy, may satisfy a polynomial of lower degree. If there is no polynomial of lower degree, then this is the polynomial of lower degree. I mean, I am not saying strictly lower degree. Might satisfy. If there is no available polynomial of lower degree, for example, I satisfies that is the only, I cannot reduce in R that degree. So if I don't know about alpha, I have no proper information about alpha, but alpha might satisfy. I have one equation that is satisfied by alpha. So there might available some new equation of lower degree. Upper degree I can produce by squaring this. This is the upper degree. So in either case, what we need to prove, that is proof. So this is the degree of minimal polynomial. Okay. That might not be this lies is actually degree of okay. So as a corollary, I can say that if A over F is a finite extension, so why? See, algebraic means every element of select alpha belongs to K. So I need to say that there exists a minimal polynomial which satisfies alpha. So I can also use this theorem. When it is algebraic, if and only if that is finite. So I need to show that that colon F it less than infinity. I will use this thing. Then F alpha is a Okay. Also, F alpha is a subspace of the vector space. They are all vector space, right? Okay. Yes. Thus, what is this thing? There is vector space dimension, but F alpha is subspace. So this dimension will be also less than by this, less than equals to, because this is the bigger vector space. K is bigger vector space. So bigger vector space dimension will be bigger, and that is a subspace. So the subspace dimension will be lesser, but this is finite. Why this is finite? Because we assume that it is the finite extension. Finite extension means the dimension is finite. Thus, K, sorry. Thus, uh, F alpha over F. So by above the position is so much write this. So I will conclude my class here. Thank you for attending.